Hi, I'm Mark Barsamian. In this video, I'll be giving a short introduction to concavity. This material is from section 4.2 of the book. More specifically, the concepts in this video are scattered throughout section 4.2, so it's difficult to give any particular subset of section 4.2 for you to read, and there are no book examples similar to the examples in this video. You do have a homework assignment, homework 57, which is this collection of 5 exercises from section 4.2. Useful concepts from previous sections will use the correspondence introduced in section 4.1, the correspondence between the sign behavior of f prime on an interval and behavior of the graph of f on the interval. That was, if f prime is known to be positive on an interval ab, then f of x will be increasing on that interval. I want to start by defining concavity, and I will give first just a graphical definition. So we say that a function f is concave up on an interval a comma b to mean this: for every x equals c, with c in that interval, the graph of f of x has a tangent line at x equals c, and the graph of f stays above that tangent line for all x values in the interval a comma b. So let me draw a couple of examples of functions whose graphs are concave up. So there are 2 examples of graphs that are concave up. Now notice that the description of a concavity in terms of the graph staying above the tangent line, there is a tangent line drawn at x equals c, and you can see that for x values near x equals c, the graph of f is definitely above the tangent line. Now this picture on the right might puzzle you because for this graph, the line is tangent at x equals c, and you might notice that the graph over here is not above the tangent line over there. Well, that's not what we're talking about when we say that the graph stays above the tangent line. What we mean is that if you look at a particular x value, the graph stays above the tangent line at that x value. So let's zoom in on an x value a little bit to the right of c. You see that for that x value, the graph of f of x is above the tangent line, above that red tangent line that was drawn over there at x equals c. That's the definition of concave up on an interval. And of course, there's an analogous definition for f being concave down on an interval. That would mean that the graph of f stays below the tangent line. Now there's a related term. What's called an inflection point is a point on the graph of a function where the function is continuous and the concavity changes from up to down or from down to up. Let's do an example involving just what we've discussed so far. So here's a graph of a function. It's the same graph that we've discussed in a couple of previous videos. Way back in video 20 when we were talking about y values on a graph being positive or negative, and then again in video 53 when we were talking about a function f of x being increasing or decreasing on intervals. And now we're going to use the same graph and scrutinize it for concavity behavior. This example is similar to 4.2 exercises that you have on homework 57. Start with question L. On which intervals is f of x concave up? Well, I'll indicate those on the graph by drawing kind of a bowl shape, kind of a bowl facing up, bowl facing up. Now we have to give an answer in terms of intervals, so we have to give the endpoints of the intervals. So those are the 2 intervals where f of x is concave up. Question M. On which intervals is f of x concave down? Well, I'll draw downward facing bowl shapes on those parts of the graph. Now we have to give an answer in terms of intervals here. Notice that I have to break this interval up into two. I cannot say this. I cannot say 6 comma infinity. The reason is there's no tangent line at x equals 9. So I cannot say that for all x values in this interval, there's a tangent line and the graph of f stays above that tangent line. There's no tangent line at x equals 9. So I've got to break my answer up into these two smaller intervals. Question N. Find the x-coordinates of all inflection points. Well, I'm going to illustrate those by drawing a blue X. Those are the places on the graph where the concavity changes from up to down or down to up. And the x-coordinates are -4, 2, 6. Question O is similar. Find all inflection points. Now, you might think at first that that's just the same question, but it's not, because remember that an inflection point is a point. A point is an xy pair, so we have to give xy coordinates for these inflection points. So that's the idea of the simplest definition of concavity in terms of the relationship between the graph and the tangent lines to the graph. Now I want to go back up to the definition and give the abstract definition of concavity. To say that f is concave up on an interval is defined abstractly this way. It means that f prime is increasing on the interval. So f is concave up, f prime is increasing. And similarly, there's an abstract definition for f being concave down on an interval. It's this: f prime is decreasing on the interval. Let's think about these abstract definitions while looking at graphs like we considered before, the hand-drawn graphs. So these graphs. I've made copies of these down below. So there are those two functions we considered before that are both concave up. Now let's think about what their derivatives would look like. So to do that, we'll think about more tangent lines on these graphs. So consider those tangent lines right at C and to the left of C and to the right of C. So in this first graph, this first tangent line is tilting down, so its slope is negative. This tangent line at x equals C has slope 0 because the tangent line is horizontal. This tangent line to the right of C has a positive slope. That means for the first function, the derivative will have a negative y value here, we'll have a 0 y value here, and we'll have a positive y value here. Because remember, the numbers that are the slopes of the tangent lines on the function are the numbers that are the y values on the graph of the derivative. Now for this graph over here on the right, all three of these tangent lines tilt down. So this tangent line has a very negative slope. This tangent line has kind of a medium negative slope. And this tangent line has a negative slope that's very close to 0. So that means the y values will be very negative, medium negative, and negative but very close to 0. So you see that both of these graphs of f prime are increasing. So this abstract definition of concavity, that f prime is increasing on the interval a comma b, corresponds to f being concave up on the interval. It agrees with the graphical definition. Let's go on. In section 4.1, we sometimes examined the graph of a function considering its increasing and decreasing behavior to determine the sign behavior of f prime. Now we realize that we can, if we're given a graph of a function, we can scrutinize its concavity behavior to determine the increasing and decreasing behavior of f prime. So here's that same given graph of a function f of x. So we want to know this. On which intervals is f prime increasing? Well, that's going to correspond to intervals where f is concave up. So we see that f prime is increasing on these two green intervals, and it's because f of x is concave up there. We have a graph of f of x. Question Q. On which intervals is f prime decreasing? Well, remember that f prime decreasing is the definition of f being concave down. So that's that interval, and this interval, and this interval. So f prime is decreasing on these three intervals because f is concave down there. Let's go on. Now, what if a function f is given by a formula, not by a graph? Is there some way to scrutinize the formula for f of x and determine the concavity? Well, it turns out there is a way. The key is to note two things. Remember that the abstract definition of concavity of f of x is in terms of the increasing and decreasing behavior of f prime. Now, think about this. The increasing decreasing behavior of f prime will be related to the sign behavior of the derivative of f prime. Now, where did that come from? Remember that if the derivative of a function is known to be positive on an interval, then the function will be increasing on that interval. Now, in this sentence, the function is f of x and its derivative is f prime of x. What we're doing here is we're thinking of the function as being f prime, and then the derivative will be the derivative of f prime. So that, again, let me say that more in a different way. We have the derivative of f prime and the issue of whether it's positive, negative, or zero, and that will tell us about the increasing, decreasing behavior of f prime. So that leads us to study the derivative of f prime. That's what's called the second derivative. The second derivative of a function is denoted f double prime of x, and it's also denoted d squared over dx squared of f of x. And what it means is this: f double prime is the derivative of f prime. In other words, ddx of ddx of f of x. So now we can talk about the correspondence between the sign behavior of f double prime and the concavity behavior of f. So here we go. If f double prime is positive on an interval a comma b, well, that tells us that f prime is increasing on the interval a comma b, which in turn means that f of x is concave up on an interval a comma b. Now there's some subtlety in this correspondence. If we know that f double prime is positive on the whole interval, then it's guaranteed that f will be concave up on that whole interval. But if f is concave up on the whole interval, it's not guaranteed that f double prime will be positive on the whole interval. We've run into this kind of subtlety back before in section 4.1. We know that if f prime is positive on a whole interval, then it's guaranteed that f will be increasing on the whole interval. But if f is increasing on the whole interval, it's not guaranteed that f prime will be positive on the whole interval. It's worthwhile to consider two examples that will illustrate this subtlety. So let's let f of x be x squared. Then let's find f prime. And then f double prime. So f prime is 2x and f double prime is 2. Now let's let g of x be x to the fourth. Find g prime and g double prime. So g prime is 4x cubed, g double prime is 12x squared. Now consider the graphs of f prime, and f double prime, and g prime, g double prime on the next page. So there are our graphs of f, f prime, f double prime, and g, g prime, g double prime. Notice that both f and g are concave up for all x values. And notice that f prime and g prime are both increasing for all x values. That makes sense because that's how concavity is defined. Now notice that f double prime is positive for all x values. But g double prime is only positive from on the interval negative infinity comma 0 and the interval 0 comma infinity. Because right at x equals 0, g double prime equals 0. These examples illustrate that for some functions, the function can be concave up on the whole interval and its second derivative can be positive on the whole interval. But there are functions that are concave up on a whole interval even though their second derivative is not positive on the whole interval. This function g is concave up on the whole interval, negative infinity to infinity. G prime is only positive on these two half intervals. On the other hand, if we know that g double prime is positive on some interval, we know for sure that the function g is concave up on that whole interval. It turns out that g is concave up on more than just that interval, but that's okay. Let's go on. So the conclusion is that appearances can be deceiving. For that reason, you have to be a little cautious trying to draw conclusions about the sign behavior of f double prime from a given graph of f of x. That caution shows up in the rather peculiar wording of some of the questions you have in your homework. The following example has that same kind of wording. So this example has we're just continuing the same example. Question R, on which intervals is f double prime positive? Well, we can see clearly that f is concave up on that interval and concave up on that interval. The confusing thing is here's a spot on the graph of f that looks like this spot on the graph of f up here, but it also looks like this spot on the graph of g up here. So in the case of the graph of f double prime was positive on that whole interval. But in the case of the graph of g was not positive on the whole interval. It was just positive on two half intervals. Well, what we're being told in this example is to not worry about that. We're supposed to assume that f double prime is positive at x equals negative 7. So if we can assume that, then the answer is we conclude that f double prime is greater than 0. That is, f double prime is positive on these two green intervals because f is concave up there. Question S, on which intervals is f double prime negative? Well, we're supposed to think about these chunks of the graph that are concave down. And again, here's this troubling spot where it looks like the graph is clearly concave down. We're not positive that that means that f double prime is negative, but actually we're told to assume that. So the answer we're supposed to give is f double prime is negative on those three intervals. Let's go on. Example 2 is similar to a couple of your homework problems. Given a graph of f of x, tell the sign of f prime, and f double prime. So for the given graphs, circle the correct word, positive and negative, in each of the three sentences, and cross out the incorrect word, positive or negative. Okay, well, in this first sentence, f is positive or negative on the interval. Well, that refers to whether f is above or below the x-axis. So the fact that f is above the x-axis tells us that f of x is positive. Now the second sentence, f prime is positive or negative on the interval. Well, f prime being positive or negative corresponds to f being increasing or decreasing. Well, we can see that f is decreasing. So that tells us that f prime is negative. Now the third sentence, we have to choose whether f double prime is positive or negative on the interval. Well, the sign of f double prime corresponds to the concavity behavior of f. F is concave down, so that tells us that f double prime is negative. Let's do the same thing for g. We have to choose whether g is positive or negative. Well, g is below the axis, so that corresponds to g of x being negative. Now we have to decide whether g prime is positive or negative. Well, that corresponds to g being increasing or decreasing. We see that g is decreasing, so that tells us that g prime is negative. And finally, g double prime, we have to decide whether it's positive or negative. Well, the sign behavior of g double prime corresponds to the concavity behavior of g. We see that g is concave up, so that tells us that g double prime is positive. Let's go on. In this example, we're given the sign of f, f prime, and f double prime, and we're supposed to sketch a possible graph of f. Well, we're told that f is less than 0, and we're told that f prime is greater than 0, and we're told that f double prime is less than 0. And we're supposed to sketch a possible graph of f. Well, let's translate this information into things that we can say about the graph. The blue information tells us the graph of f will be below the axis. And the green information will tell us that the graph of f is increasing. And the red information, that f double prime is negative, tells us that f is concave up. So we need to draw a graph that is below the axis but increasing and concave up. There is an example of a graph that does that. It's below the axis, it's increasing, and it's concave up. That's the end of the example, and that's the end of the video. Thank you.